Well, by my calculation, this is 3 p.m. Eastern. So I see that we have 8 participants in Zoom. In the interest of time, we should get started. More people might come, and whether they come or not, it doesn't matter. We are recording, and this is going to be posted and available on the QED-C website. So on behalf of QED-C, my name is Adrian German, and I want to welcome you to this 20th session of what used to be called Student Research e-poster sessions and is now Quantum Talent Showcase. This session was, this series was started back in June 2020 by the then chair of the Workforce Development TAC of the QED-C, John Candelaria, and we're now in session 20. And as I said, more people might come and join us. Today we have 2 presentations. I'm going to start introducing the first presenter. I'm looking for the second presenter. There he is. I'm going to quickly interrupt what I'm saying and ask Alan if he wants to make a quick test of screen sharing. Would you mind? I see the second presenter there.
Sure, I can screen share.
Yeah, that's what I'm saying. I stop my share, my screen share. Can you share your screen just to make sure that we are in good shape?
Right.
And then I'm going to introduce, after we make this little test, I'm going to introduce the first presenter and we're going to get started.
Okay, can you all see this?
Yeah, so it's not in presentation, but we can see the main slide and the other slides on the left.
Is that good?
Yeah, yes, that was
Great.
Perfect.
Awesome.
All right, so this is being recorded, and let me share it again to welcome you again. And at this point, we have 13 participants, and as I said, things are going to just happen. So the first presenter is Leon Chen Ding, who is a recent graduate of the engineering quantum systems group at MIT, which is a lab specialized in superconducting qubit experiments supervised by Professor Will Oliver. During his PhD, Leon developed the infrastructure to design and measure Fluxonium qubits and demonstrated state-of-the-art single and 2-qubit gate fidelities. Leon now works at Atlantic Quantum as a co-founder, a startup working toward building scalable quantum computers with the Fluxonium qubit. I just want to briefly tell about him as we switch from my presentation outline to his slides. He's the winner of the 2020 IBM PhD Fellowship Award. He graduated from Caltech in 2017 with a double major in physics and computer science, and worked in between undergraduate and graduate studies he worked in San Diego at Trex Enterprises. So with this, go ahead, take it away, Leon.
All right, hello, can you hear me first of all?
Mm-hmm.
Awesome. I'm very happy to be here. My name is Leon Ding. So today I'll be talking about a high fidelity, frequency flexible 2-qubit Fluxonium gate with a Transmon coupler. But before getting into too many details, I just want to give a brief overview of superconducting qubits for those not as familiar to the field. So to start off simple, the most simple circuit that you can build out of these circuit elements is the LC oscillator. So this is just a capacitor and an inductor placed in series. So in principle, current will flow back and forth across the circuit, oscillating at a particular frequency, but because of the parabolic nature of the inductor's potential energy, we can see that all the energy levels of the system are evenly spaced. That means if you drive one transition, you will actually drive all of the transitions, and therefore the system is not actually suitable for trying to form a qubit. And for a qubit, you need 2 energy levels that are completely isolated from the rest of them, or at least directly addressable. So to the rescue comes this Josephson junction component. So this is, I would say, the key component for superconducting qubits. And it is key because it supplies a nonlinear potential energy. As you can see here, its potential energy is a cosine instead of the parabola here. Just get the laser pointer. And it is formed physically by sandwiching a very thin insulating barrier around between two superconductors. So how does this help form a qubit? So if we just simply replace the classical inductance with this Josephson energy in our previous harmonic oscillator, we get a just normal capacitor and now this Josephson junction. So this cosine creates like a slightly anharmonic perturbation on the normal parabolic potential of the inductor. And this changes the energy levels just very slightly, such that the energy levels of the system are all slightly different. And as you can see here, as you go up in energy, the energy spacing between levels gets slightly smaller. And this is enough to isolate the first ground and excited states of the system to drive and form a qubit. So to this day, the Transmon is the kind of the most common or like status quo qubit used across labs and companies in the field of superconducting qubits. But beyond the Transmon, you can combine these components and kind of almost arbitrary arrangements to form a wide variety of superconducting qubits. So one example is the Transmon that I just talked about. You can also form like flux qubits. Specifically, this is a drawing of a capacitively shunted flux qubit. And more pertinent to the talk I'll be giving is the Fluxonium qubit. So how does this all look like in practice before getting into the details on my project is, so we have a bunch of these circuits that I just, drew on the previous slide, and these are physically fabricated on small and thin chips. As you can show here, there are also a bunch of meandering control lines in this picture corresponding to lines for control of the qubit or readout of the qubit. And then this chip gets placed inside of a package, and then the package gets placed at the bottom of what we call a dilution refrigerator, and this is able to cool down the chip down to millikelvin temperatures. So how does it get cooled down? So first it gets canned up, then it gets pumped out and then cooled down to the 10 millikelvin, and then we are able to interact with our qubit through room temperature electronics equipment by connecting these electronics to the top of the fridge. And there are lines that go from the top of the fridge all the way down to our qubit, and we interface with these control electronics with just a normal classical computer. So now, what is more specifically a Fluxonium superconducting qubit? Kind of the topic of my work here. So here is first the Hamiltonian and circuit diagram of a Fluxonium qubit. So this part is just arising. This part is just arising from the capacitor. This part is the inductive potential arising from this chain of junctions here, and this part is the potential of this small Josephson junction. So a more realistic image of a Fluxonium can be shown here, and I will try to identify the components piece by piece. So first we have shown in blue, this is a long array of Josephson junctions, and it's long enough to essentially approximate a very dense classical inductance. So as you can see here, for the most part, you can just think of this as a classical inductance, and it's formed by junctions just to get the inductance very dense. Then finally shown here, there is a one singular small junction, often termed the black sheep junction, and is labeled by this term here, EJ, for the Josephson energy. And then these two large kind of capacitors or metal pads on the outside form the capacitance denoted here by the charging energy of the qubit. And of course, this qubit technically forms a closed loop. That means that you can tune the properties of the qubit by threading flux through this loop shown here. And this is just a diagram or plot of a few of the energy levels. So the 0-1 transition, 0-2 transition, and 0-3 transition as a function of the external flux through the loop. And what are some of the key properties of Fluxonium that differentiate it from the more traditional Transmon superconducting qubits? Well, first is that it has a particularly low frequency at the sweet spot, and this sweet spot is just determined by the second order flux insensitivity point at 0.5 flux quantum here. And so typically these frequencies can be under 1 gigahertz. And this is in contrast to Transmon qubits, which have frequencies between around 4 to 6 gigahertz in practice. This qubit also has a very high n-harmonicity. So while the 0-1 transition is just a couple megahertz in this plot, the 1 to 2 transition is around 5 gigahertz. And because of the low frequency of the qubits, Fluxonium has been able to demonstrate upwards of millisecond coherence times, both T1 and T2 in various groups. So with the introduction to Fluxonium out of the way, I want to kind of just set the stage and just talk about the current landscape of 2-qubit gates with Fluxonium qubits. So the two broad classes are computational state gates and non-computational state gates. So for computational state gates, the population of the qubit remains in the computational states throughout the duration of the gate operation. And this is, of course, good because the lifetimes of the computational states of the Fluxonium are much larger than the lifetimes of the non-computational states. A subtle drawback to the scheme is that due to the kind of protection within the computational subspace, you naturally have smaller charge matrix elements, and this reduces the coupling both to control lines and coupling to other qubits, so that it becomes a lot more difficult to actually realize fast gates using computational state gates. Non-computational state gates, on the other hand, use as its name suggests, non-computational states, so 2 or 3 or etc. states as an intermediate during the gate operation in order to facilitate a 2-qubit gate. And one good thing about this is that you can have the actual, computational subspace of the qubit very well protected. So very well protected 0-1, and this won't actually hinder your 2-qubit gate performance because you will use other levels in order to facilitate the 2-qubit gate. And of course, the most obvious drawback about the scheme is that now, because you are populating higher levels of the qubits, these higher levels have much worse coherence times than your computational state, and your gates will typically be limited by the coherence times of those other states. And a challenge for all systems is to mitigate the always-on ZZ, which is just a continuous residual entangling rate between the qubit, between the two qubits, as a result of coupling. So for our project, we will show a non-computational state gate with high fidelity and a robust ZZ mitigation. So we'll start with the 2-qubit version of our gate. So if we have 2 qubits coupled here, such that these two states are close in frequency and are therefore hybridized and have a level repulsion with each other, we can selectively drive a 2-pi pulse between this 1-1 state of the 2-Fluxonium system to either this state or this state. And as you know, after you drive a 2-pi Rabi oscillation, you don't exactly come back to the initial state. You have this -1 phase accumulation on the initial state. So as long as you drive one of these oscillations for a 2-pi pulse selectively, you get a -1 phase shift on the 1-1 state, and this realizes the CZ gate or controlled Z gate. So for our scheme, we will introduce a tunable Transmon coupler between these two states, such that now the three relevant coupled levels are this 2-0-1 state of this 3-qubit system, the 1-1-1 state, and the 1-0-2 state. And similar, same as before, if we drive a selective 2-pi pulse from the 1-0-1 state to any of these 3 states, where it should be able to realize a controlled Z gate. So just to illustrate this in a different way, so here is an energy level diagram of these 3 relevant states, this 1-1-1 state, 2-0-1 state, and 1-0-2 state as a function of the coupler flux, which is in this case here, this tunable Transmon. So as a function of flux, we should be able to drive any of these transitions in order to realize a valid CZ gate, or any of these transitions, or any of these transitions. So to summarize the introduction of this tunable Transmon coupler, so it provides strong couplings in the non-computational state manifold to help facilitate the 2-qubit gate. The tunability further allows for a flexible gate frequency, and this is very important for microwave activated gates. Otherwise, a lot of the times, your operational frequency becomes set by the fabrication parameters of the qubits. And once you put it in the fridge, cool it down, oftentimes you cannot tune this frequency anymore. And if it so happens that there are collisions with other qubits or two-level systems at that frequency, the inability to tune the gate frequency will kind of render the qubit unusable. And as we will talk about later on, this tunable Transmon coupler also provides a means to mitigate the always-on ZZ interaction. So here, this is just a picture of our device. So the zoom in here is we have two fluxoniums in red on the outside, capacitively coupled in the middle to this tunable Transmon coupler. And for the most part, all qubits have individual readout lines, charge lines shown in green, and flux lines shown in purple. All right, so to talk about the ZZ reduction in our system, we model our 3-qubit system with this Hamiltonian shown here. So this is just the Hamiltonian for the Fluxonium 1, Hamiltonian for Fluxonium 2, and the Hamiltonian for the coupler. And then we just have pairwise capacitive couplings between the two qubits. So the JC is the capacitive coupling between each Fluxonium and the coupler, assumed to be equal for the purposes of this analysis. And then we have J12, which is the capacitive coupling, but directly between the two Fluxonium qubits. And the quantity of interest we called ZZ is precisely defined by this equation here. So this is the frequency of the 1-1 state of the two Fluxonium system minus omega 10 minus omega 01 plus omega 00. So to build up the system, when we just have two Fluxonium qubits, there's only a second order or the second order interaction between them produces a negative ZZ. And this is because all the higher levels of the Fluxonium are positive, and you can think about this as these higher anharmonic levels will push down onto the computational states to produce a negative ZZ interaction. So surprisingly, to third order with the introduction of the coupler, you can get these sort of level pulling effects, which are traditionally non-intuitive. But in this case, we found that they can lead to positive contributions to the total ZZ. To fourth order again is the normal scenario where you just have a smaller negative correction on the ZZ. But because of this one positive contribution to the total ZZ, this gives us a mechanism to try to tune these different contributions in order to minimize the undesired ZZ as much as possible. So we do that here. So this is a numeric simulation of the ZZ in our system as a function of the direct Fluxonium coupling strength on the x-axis and the Fluxonium Transmon coupling strength on the y-axis. And as you can see here, there is a very large band in white where the ZZ is very, very small. And our device with the experimentally fitted parameters lies around here, extremely close to this kind of ZZ minimum. Though we'll note that this ZZ minimum is incredibly broad, so some sort of normal variations or uncertainties in these parameters will still put you in a very good regime for the ZZ. And of course, the proof is always in the pudding. So these are our experimentally measured ZZ values in our 2-qubit system as a function of the coupler flux. So this is just saying that for the entire range of the coupler flux, the ZZ is extremely close to 0. So in this case, between 1.5 and 2.5 kilohertz. And because it's low for the entire coupler flux range, basically any value of the coupler flux is acceptable for operating the system. But the important point here is that we can always pick coupling strength values such that the ZZ in the system is near 0 across a very large coupler flux range. So to now talk about the single qubit gate performance in our system. So here were the rough qubit specs for the final paper device that we used. We have 2 Fluxonium qubits with rather low frequencies. This one is around 300 megahertz. This one's around 200 megahertz. So for our Fluxonium 2s, we often get around 1 millisecond T1s. And across all devices for Fluxonium 1, we found slightly lower T1s, and this is presumably due to the different parameters or higher frequency of the qubit. But despite having, in this case, up to millisecond T1s, we do not have millisecond T2s, and this is still kind of current work to understand why the T2s are much less than the T1s. The current suspicion is photon shot noise in the resonator, resulting in kind of decoherence for the qubit, but this is definitely still an area under active study for us. So here I'm just illustrating, these are, we have single shot readouts of the 2 qubits in our system, and our typical kind of readout fidelities are about 95 to 99%. Because of the low frequency of these Fluxonium qubits and thermal equilibrium, we have like a decent thermal population, near 50-50 thermal population between the 0 and the 1 state. So we also use single shot readouts to initialize the qubit in either the 0 or the 1 state. So this readout fidelity is also, in a sense, our initialization fidelity for our qubits. So our highest T1s was on actually a backup device here. And in this data set, we had measured the T1 for around 8 hours, and we found like a median T1 of 1.26 milliseconds. These were the highest kind of T1s we measured in the system or in the group in general to date. But at least for the main device, for single qubit gates, we found the single qubit gates optimized around 18 nanoseconds, and we performed both individual Clifford randomized benchmarking on the 2 qubits, as well as simultaneous randomized benchmarking for the 2 qubits at the same time. So shown here, the individual randomized benchmarking, we have 99.99% fidelity. This is the average single qubit gate fidelity for each of the 2 qubits. And then when we go to simultaneous randomized benchmarking, the fidelity only suffers by a very, very small amount. And this is attributed to the very low ZZ in our system, which allows us to kind of do our gates simultaneously or in parallel without any significant reduction in fidelity. And at least for now, as far as we know, these are the highest coherences as well as single qubit gate fidelities on any 2D coupled qubit device. So back to the 2 qubit gate. So as I mentioned before, we are primarily interested in the transitions from the 101 state of the qubit, and we drive to either of these 201, 111, or 102 in order to realize a CZ gate. So here are the transitions coming out of the 000 states. These are the transitions coming out of the 100 state, 001 state, and the important one, the transitions coming out of the 101 state. So here, these are the 3 transitions shown here. And again, as I mentioned before, in order to really faithfully do a 2 qubit gate, when you drive a transition, it needs to be selective. So for example, that means if I drive this transition here at 0.5 phi naught, the same frequency better not be resonant with any transitions starting from any of the other initial states. And this is kind of illustrated here. If we start in any of these other initial states, the same drive frequency is off resonance with any transition of the system. And the time domain kind of like oscillations of this interaction are shown here. So we activate the gate by charge driving both of our Fluxonium qubits. And this is the kind of the population oscillation as a function of the length of the drive when we drive this point. Okay. So now the first big result, I would say, of this experiment is that we demonstrate a gate calibration as a function of the coupler flux. So just to make it simple for this plot, all pulses use a 100 nanosecond cosine pulse envelope, and we just linearly sample the flux 21 points across each of these transitions. So this means we're calibrating a gate across all the points here shown by this animation. And the final results are here. So the blue points are this bottom transition, the purple points are this middle transition, the red points are this top transition, and we show kind of data for both of the devices that we had in the fridge at the time. And we note that there are many frequencies where the gate was kind of the previous state of the art for Fluxonium. So before this experiment, the highest 2-qubit Fluxonium gate fidelities were around like this 99.6 to this 99.7. So now in our system, we are able to achieve that and also exceed it for a wide range of gate operation frequencies. And this is also without optimizing for the pulse time. So for this plot, all of this gate calibration was kind of run automated, and there was no hand tweaking or hand calibration. And of course, there are a couple points that are missing from this plot that are resulted from like a failed calibration from the measurement automation, and this can fail for a variety of reasons, such as just breaking of the code or just accidental resonances with higher kind of multi-photon transitions. But the important point is that we can get a high fidelity at a large kind of range of different operation frequencies, and it's not just one frequency. So if we want to optimize the gate even further, we first identify a point where the fidelities seem kind of rather high already. So at least for this demonstration, we identified this point as kind of already working well without optimization. And then we kind of scan the fidelity as a function of the pulse width to get a sense of when the coherent and incoherent errors of the system begin to trade off. So here, this peaks at around 99.89% fidelity. And to optimize that a little bit further, we implement reinforcement learning on the pulse shape directly. So here, in the dashed is kind of an illustration of the kind of nominal base pulse shape, and then in the solid lines is the representation of the pulse shape after the reinforcement learning. So this was shown here. This is our kind of like best run of the reinforcement learning. We're able to get a kind of consistent but small increase in the fidelities as a result of this reinforcement learning, and our kind of best training run is shown here in the orange, and averaged all together we get a 99.92% CZ gate, and this was done at 50 nanoseconds. So this is notably faster than our kind of previous calibration. This we call the kind of physics-based calibration. So this is faster than the physics-based calibration can handle, presumably because of very subtle effects that are kind of break the automation code, but the reinforcement learning agent is able to figure out and make it work. In conclusion, we've introduced this kind of FTF coupling architecture, which has benefits in reducing ZZ. It also mediates kind of hybridization or couplings for non-computational state gates. And we've demonstrated state-of-the-art T1 times in planar qubits, single qubit gate fidelities, 2-qubit gate fidelities, at least for a kind of 2-qubit system level. We've shown a frequency flexible and easy to calibrate 2-qubit gate, and kind of to try to like back up the claim that this is kind of flexible, robust, and easy to calibrate. We show a device from we showed data for both of the devices that we had in the fridge at the time. So our results are on the archive as of a couple months ago. So please, if anyone has questions, like feel free to check it out and email me for any questions. And finally, I just want to acknowledge and thank the entirety of the MIT Engineering Quantum Systems team, as well as MIT Lincoln Laboratory. Thank you.
A wonderful presentation. Thank you so much for this. So in terms of time, we have, I mean, you finished exactly on 30 minutes. We have at most 15 minutes for questions, and then we would have another 30 minutes plus 15 at most question and answer for two presenters, because we have a 90-minute period of time. We don't have to have questions 15 minutes, but if anybody has any questions, this would be the time to ask them, please. You can ask them by speaking, because you can unmute yourself. So there is, I think Alan is applauding your presentation, as we are all. And then anybody who wants to speak or write in the chat. Any questions?
May I go ahead and ask?
Please.
All right. Thank you very much for a great talk, Leon. It's beautiful work.
Thank you.
This is an exploratory question in a sense. Do you think you could use an architecture involving the Transmon coupler for having, instead of a second Fluxonium on the other end, maybe a harmonic oscillator for bosonic control?
So you're saying instead of the Transmon, have a harmonic oscillator or something like that? Or are you saying instead of the second Fluxonium qubit?
Instead of the second Fluxonium.
Instead of the second Fluxonium qubit, this I will say I can't answer. Yeah, sorry. Like don't have too much experience with like kind of different types of qubit architectures, such as bosonic modes, mainly just dealt with kind of like Fluxonium gates. But is there like a specific property that you would be looking for, kind of in relation to these kind of other systems or other use cases that you have in mind?
Well, I'm still learning myself, but
I see.
what was on my mind there is thinking there's very high single qubit gate fidelities for a Fluxonium, and then there might be some challenges with using a Fluxonium directly as an ancilla on a gigahertz frequency oscillator, like perhaps as a quantum memory. Maybe if there were a nice coupling scheme, that could be useful.
Yeah, I think it's possible, but given that the very different nature of like the bosonic systems and their very different requirements, it probably will not just be just like a kind of plug it in and have it work. Like I think if you want to have coupling to the 0-1 states of the Fluxonium, then you might need to think of some different strategies, because in at least the FTF coupling scheme, the Transmon is supplying coupling with the higher levels of the qubits and not actually the computational states. So if you find some way to kind of mediate coupling through the higher levels, then there is presumably some way to utilize the Transmon.
All right, thank you.
I think I have a question in the chat. Thank you for the presentation. Does MIT offer traineeships for CSU students, BS in advertising, working on MS in mass communications, AS in engineering, and AS in electronics, looking to earn a MS and then a PhD in quantum technology? Thank you. So as far as I know, so I don't know of like kind of like a general program by MIT. Maybe there is one, but a lot of the time, or at least the way things work with these labs is like if you can get in touch with the professor and then the professor is willing to have you, then you can kind of like come for like a summer internship and then work there and kind of develop relationships with the people at the school or in the lab. But this is generally kind of with the professor's permission and not like by some MIT as a whole program. So at least for my specific lab, I'll say like, if you talk to Will Oliver and you get him to say like, yes, I'd be happy to, have you come intern, I can, pay for your internship, et cetera, then I presumably that should, kind of be enough. But yeah, I think you would need to go to the professors of the groups.
Right. So I want to add something. So if you're going to talk to Will Oliver, the first thing he's going to ask you, have you taken our certificate program? So I'm not sure. MIT X Pro, right? He has 2 programs in 4 chunks. Each one is a month. And Will Oliver, to my knowledge, has been a keynote speaker at Q2B since, I don't know, 2018. I remember he used to say, we need a quantum engineering textbook. Somebody has to write it. Has he written it? Do you know? Has he written it already?
We don't have a textbook, no. We have like a very kind of well-cited and semi-recent review paper for kind of superconducting qubits. I would say maybe it's like halfway in between like a paper and a textbook. So not enough to, kind of sit down with nothing and learn everything, but with some kind of knowledge of the field, it's a nice overview and kind of summary of kind of relevant frontiers and how working principles of the field. But in terms of like a full-on textbook, I'm not sure of one.
Okay. So there is a textbook currently.
Okay.
One thing I know for sure is that Zatko Minev, who was at IBM and he graduated at Yale, said that he is working on a textbook with I forgot his first name, Devoret, who is who's credited with the invention of the superconducting qubits. Then there is a second book that came out like last year, and it's from somebody at North Carolina State. Again, I forgot. So there are some textbooks, but well, let me follow up unless somebody has any. Let's see. How about we read the question by Colin? Thanks for the talk, quite interesting. Less directly related to your talk, but given your expertise working with superconducting qubits and related architectures, what are the viability of superconductive quantum computers in industry and startups as opposed to photonic or neutral atoms or trapped ions? What are the trade-offs that you are seeing? How about you give that question a shot, please?
Yeah, so I guess kind of given the nature of this question, this will be more of like just like a personal opinion. But yeah, so I guess 2 big points that I would kind of emphasize. One is that all architectures are, I would say, not very close to realizing kind of like, useful or profitable quantum computing. So in that regard, I would say that kind of, no architecture is like so close where you'd say like that one's gonna do it. It's very productive for all architectures to kind of exist and kind of work towards the same problems, just for us as a field to just get more experience with the oncoming challenges of trying to realize larger scale quantum computing. So there are, of course, like pros and cons, but I wouldn't say one of them is like, oh, this platform is definitely going to do it. I think it's all very productive for all of them to exist and learn from each other. But in terms of an actual difference, if I must say something, to me, there's kind of a spectrum between like, superconducting qubits and these ions or neutral atoms that you mentioned, and that for ions and neutral atoms, I like to think of them as maybe like kind of like the most pure or like very pure qubits, where you're using qubits out of systems that were kind of like existing existing by nature. Like if you're using some transitions out of an atom, it's like every single atom behaves this exactly the same way, and then this atom is a very clean system kind of given to you by nature. So for at least atoms and ions, you have like very, very nice kind of pristine qubits. Whereas for superconducting qubits, you're kind of like with a, technology of like with the silicon technology, you're able to like, precisely fabricate a bunch of metal in some rearrangement to like form some circuit to kind of mimic a qubit. So in some sense, it's a less pristine qubit. It is like big. It is like kind of forms of like 10 to the 26 atoms, not like one atom. But because it is using kind of this very mature human technology of just like, printing like akin to like printing computer chips, it has a very kind of significant advantage in terms of like scalability and like design flexibility. So if you want qubits at particular frequencies and you want to specify the frequency, superconducting qubits can do that for you. If you just want to like arrange qubits however you want, make whatever you want, and kind of like configure them however you want, the technology of superconducting qubits is like very conducive to that. So that is, at least to me, like a rough trade-off across this spectrum of different platforms.
Okay, I have another question. What are the challenges that you need to solve for scaling the superconducting qubits to a large system?
Yeah, so this is a tough question, and there are challenges that we know, and then there are challenges that the field as a whole we don't even know yet. But yeah, so there's like some of the challenges, just to name a few of the most kind of immediate ones, is just that when you make larger and larger systems, it becomes harder and harder to control the qubits. Like if you have kind of, residual coupling between two qubits very far away on the chip, that makes control all a bit harder. If you need all the qubits, to work at the same time, then you need to like have like increased demands on fabrication yield. If you want like 1 million qubits and you want to control them all, then at least for superconducting qubits, this is like a very serious requirement in the amount of like wires and cables that you need, and then like classical control electronics that you need. To just give an example of this, is at least like basically to control every qubit, you're basically using like a full like classical computer to control one qubit. And if you have like 1 million qubits, are you going to have like 1 million classical computers? It's like probably not. So there are a lot of scaling inventions and stuff needed in order to like even scale down the classical technology to even like physically have a larger quantum system. And of course, for things like error correction, and then like high enough and to get like high enough gate fidelities to do something useful, it requires like kind of larger fidelities for single 2-qubit and readout operations than I would say we have today at a large scale.
Okay, so I'm going to try to ask one last question. It's my question, and it's based on the fact that your background is physics, that's the major, and computer science.
Yes.
So you see, qubits are mostly used for quantum computation, and computation has to do with computer science. So I'm asking a computer science student that isn't part of a physics program or a chemistry program or an engineering program specifically, would they have any hope to have a quantum hardware lab of some sort in the next 5 to 10 years, like you as a undergraduate student, without the access or the exposure to physics? Would you have been able to work on a project like this? I'm looking at the picture of your lab, and there are some undergraduates. Do you think that for that we will need to have an quantum engineering department, or can that be achieved in computer science undergraduate programs, perhaps using for superconducting Qiskit metal?
So are you saying like just like
how can we involve the undergraduates?
Okay, wait, so why do we should address the big question here? Like, on one, are you talking more about like how are we going to volunteer? Like the projects or people?
Jamie. Jamie, how are you? I think we lost Jamie, or Jamie muted. Okay, well, maybe that was a, so what I want to know, to what extent and how soon can we involve the undergraduates to work on projects of the kind you are developing now as a PhD student or a postdoc, let's say?
Yeah, I think to the hardware level is actually like a bit tough without kind of physics background, I would say. So if the desire really is to do quantum hardware, I would kind of say you need to, you know, take classes in quantum mechanics and then become familiar with quantum mechanics first. There are ways to become involved with quantum computing though without needing to kind of like be deeply involved in the physics side of it. So of course, as you said, like quantum computing is like both physics and also kind of like information and computing.
Yeah.
So there's a lot more theoretical aspects to it that's a bit removed from the physics. So like kind of quantum information science, that field as a whole is a little bit removed from the physics and a bit more heavy on like the math and theoretical computer science. But I would say if you want someone to like have expertise and work on, I guess, similar to, you know, this project, you know, really nitty gritty stuff with the hardware, I think you need some sort of physics.
I understand.
Background.
So we would need a new kind of major that at this point looks interdisciplinary, and then it becomes its own major. Okay, well, thank you so much. And sorry that we're running out of time. I appreciate you coming here in the presentation and answering all the questions. I don't know, please join me in thanking the presenter for being so kind to come and give a presentation. We need to move to the second presenter so we don't run out of time. So once again, thank you so much. And I'll briefly introduce the second presenter. I guess what I'm going to do is I'm going to share the screen back to the slide that introduces everybody. And we're now going to hear from Alan Pierre-Louis, who is a graduate student in, he's a GEM fellow and a second-year master student at Stony Brook University studying nuclear physics. He works with the Brookhaven National Laboratory and the Stony Brook Center for Frontiers in Nuclear Science under Professor Abhay Deshpande, and currently is involved with the Molar experiment at Jefferson Laboratory. He's published research on the Electron-Ion Collider to be built at BNL, which is the subject of today's talk. He has several awards, and he's supported by the Edward Boucher Initiative from the Center for Frontiers in Nuclear Science. Without further ado, Alan, please take it away.
Thank you for that introduction, Dr. German, and thank you for the invitation. I will share screen right now. Okay, and then please let me know if you are seeing the screen, and I will go to the beginning.
Yeah, I see it. Good. Wonderful.
All right. Thank you, everybody. Thank you for this introduction. So the title of the talk is Feasibility of the Elastic Electron-Proton Cross-Section Measurements at High Q Squared. So that is a mouthful. Basically, what is being discussed in this talk is the fact that currently there is a relativistic heavy ion collider, basically a large collider experiment at Brookhaven National Laboratory, and it's an apparatus that is abbreviated to RIC. On top of this, and replacing most of its parts will be the EIC, or Electron-Ion Collider. And this will collide ions with electrons. It is likened to having a CT scan on protons, so we can see the insides of them. And I'll discuss more of the fundamental physics here. So first, I just wanted to acknowledge Brookhaven National Laboratory, Stony Brook University, the Center for Frontiers in Nuclear Science. They've all been very helpful to me, thanks to my advisor, Professor Deshpande, and Barak Schmuckler, who was the postdoc who actually was my main collaborator, as well as my other collaborators, and the GEM Fellowship for their support as well. So getting into the science here, This talk is a little bit more on the side of high energy, and its relation to quantum science or quantum mechanics really has to do with quantum chromodynamics, or QCD. Quantum chromodynamics basically describes the strong force within that interacts with particles like the quarks and gluons, which make up constituent particles. They are the constituent particles for things like baryons. So baryons, as shown in the illustration, can be seen such as the proton and neutron. They're composed of 3 quarks, and then they have gluons that attach these to one another. These quarks can be described by Dirac force spinors with several properties. And as a brief introduction to that, that basically comes from quantum field theory, and it describes all fermions except neutrinos. So they describe things such as electrons and quarks, which will be very important in this talk. This is more giving us a fundamental understanding of quantum mechanics. This is a portion of it that we don't understand too well. So hopefully in the future, there will be some application directly to quantum sciences that are more covered in these talks, but this is a very fundamental level, I would say, not so much applied. So one property that these quarks have is color, and that is basically how we describe the color charge or the strong interactions that happen between the quarks. So going further into it, QCD is what establishes quarks and gluons as having this color charge. It doesn't correspond to real color, but it is something that we use to identify the charges in this scenario. And basically, there are things that we don't understand too well about this regime. Gluons interact with each other as a result of the mathematics of quantum field theory at this level, and they generate a lot of the nucleon mass. The nucleon mass, so within a proton or a neutron, all the mass is not just made up of the quarks as what was previously understood, but there's actually a lot more happening in the regime of gluons that we have yet to understand. There's gluon domination occurring. This becomes manifest at high energies and high speed, near the speed of light, and we have certain collisions at experiments like Hera, RIC, or the Large Hadron Collider in Europe. The EIC will study this further. And the context of this experiment basically is that these different collisions, which not everybody may be familiar with, but these different collisions grant us information about new physics potentially, right? So for example, we can study proton behavior and then understand form factors, and form factors can help us to understand properties like charge and current distribution. So basically, this study that we did uses a lot of statistical methods and simulation to try to separate elastic collisions from inelastic collisions. And I will go into further detail about the differences between those two. And we're at a certain Q squared value, or form momentum squared transferred. So just think of it as a certain energy. And these are the highest energies achieved that we're studying here. And it'll tell us about particle behavior at these thresholds and how we should approach things in the future. So basically, we used an elastic generator and Pythia to give us 100 inverse femtobarns worth of elastic events. What does that mean? Basically, we use Pythia, which allows simulation data. It gives us very fast approximations to generate events, or generate these collision events to simulate them. And then when we say that we smeared them, we mean that we allow for rapid and approximate estimates of the effect of detector acceptances and performance on physics observables. basically the smears in the code represents various acceptances, such as continuous regions of energy, angle, things of that sort. And then when we look at the observables there, then we get information. And this slide, it repeats that, but basically we're showing here that from the regions that we're looking for, so greater than 5 GeV squared, which is an energy measurement, all the way to 40 GeV squared, which is the higher end of the energy. The first plot is showing like its events versus the Q squared value, that these events exist. We have very good data that these events exist and are covered. Then we have the eta, so angle within our detector versus Q squared, so versus this energy region. And it gives us more insight into the acceptance ranges we'll find in the study. So again, like we see that these events exist and will be able to be studied. And we're going to see later how we restrict this data. So in order to observe what we are considering and to understand it, we have to reconstruct the kinematics. So the kinematics, of course, deal with the mechanics of the situation. We have an electron going against a proton. And usually the typical method would be you use the scattered electron method, meaning that you detect for the electron that was just hit. But sometimes that does not work all the time. There could be no detection of the scattered electron. Maybe there was no scattered electron in the case of other collision types, or maybe it just wasn't reconstructed well in the first place. We need final hadronic state information in those cases. So we need the proton information. So we have 3 different methods. We have the scattered electron method, which was mentioned before, Jacquet-Blondel, which only uses the final hadronic state information. So just looking at the proton. And then we have double angle, and double angle uses both the scattered electron and the final hadronic state information. So also the proton in this case. And then we graph the Q squared values of the reconstructions against true Q squared, or the Q squared that we got before. And this is a nice schematic here showing that the eta ranges, our study really went from negative 3.5 to positive 3.5, but basically this is a measure of angle. There is a lepton end cap, hadron end cap, and a central detector. Basically, this is a visualization of what's going on inside of the detector. And on the left, on the top, you can see that this is a proton beam. And then on the left at the top, you can see an electron beam. They're directly opposing each other. And we're considering the highest Q squared region here in our experiment. So we now get to the reconstruction of these plots. There's several equations at the top, basically for each method that I mentioned. So Jacquet-Blondel would be the first one, which only takes in proton information in this case. Then we have the Q squared versus true Q squared for the scattered electron method, which only uses the electron information. And then we have double angle Q squared versus true Q squared. So that seemed to be have the most agreement. And we see that this last method had the most agreement. The equations at the top, we can understand the Y to be the inelasticity variable. So basically, it is the fraction of initial electron energy that's lost during interaction in the rest frame of the proton. And then we would see that the alpha is the fine structure constant, which we might be familiar with in maybe quantum optics or other quantum mechanics courses. And then the MP would be proton mass in these cases. And the X is Bjorken scaling. So that is a scaling variable for our particles. For elastic events, this X will equal 1. Then we do the scaling variable versus the true Q squared, and we do it for each method again. We see that at the right, the scattered electron method is very messy. Same for Jacquet-Blondel, but double angle seems to be in very good agreement. So now we're going to consider background. Remember that I said in the beginning of the talk, what we're trying to do is show that a certain case of events or certain case of collisions can be studied at the EIC. It's a future EIC. These are all simulations. So what we're determining is at these energies, can we study a certain class of events that we want to study? A certain case of collisions called elastic collisions, which means that when the electron hits the incoming, when the electron and proton hit each other, basically the end products at the end are simply an electron and a proton again. There is no collision that results in some sort of breakup that generates other particles. And it is not trivial to assume that we're going to get the same end products again. There are several cases where we can get other types of particles, such as the nature of high energy physics. So in order to account for this, we have to do a lot of important statistical cuts and to the data. So basically, we're trying to observe that we can see elastic events and we can separate proton and electron varieties of or other varieties of particles that are from other collision results. So we confirm that we're out of the range of pion production, which can be confused for one of our particles. We eliminated scattered electrons from other types of collisions, like inelastic events. And then when we're talking about the electrons from other inelastic events, because you may ask, how can we separate an electron that came from some inelastic event where, you know, there's multiple other particles being formed? How can we separate that from the normal electron that's just scattered off of a proton? Well, there's methods to do that, but they were generated along with elastic events in the same Q squared range, so the same energy regime that we're talking about. So the statistical vetoes that we did to do this, or these cuts, these criterion to make sure that we are observing what we need to observe for this experiment, we made it so that events contain only two particles, which are the scattered electron and a proton. Two particles. The electron and proton are coplanar, so that that coplanar phi cut, or cutting along that that variable, is important. The electron and proton transverse momenta balance, you know, they're going right at each other. That should make sense. Total energy of detected electron and proton has to be confirmed, and the total Z component of their momentum has to be confirmed. So when we do cuts of this variety for Q squared over 0.5 GeV squared, so over a certain energy level, we see that we're able to generate 100 million events, and the cuts do a good job in reducing background and making sure to say, after generating these events, we're avoiding mix-up, or avoiding, mistaking some other events for the events we're looking for. Another example we have here is pion production versus elastic electron range. So the negative pions have the potential of being mixed up with the elastic electrons. But we show here that from the cuts and the eta ranges, that from this yield chart and the versus momentum, that we consistently find in these different angle ranges for eta, which can be seen in the top right corner of each of these figures, that we consistently find that the elastic electron range is outside of the negative pion range. So there's no overlap there. We have successfully evaded mixing these two up. We won't find that they overlap. Same for positive pions and kaons versus the elastic proton range. So in an elastic collision, we find that we might mix up maybe positive pions and positive kaons with the proton that's just scattered off, right? But again, we find that at these various eta ranges, we see that there's no overlap. So the elastic proton range is well out of range of the positive pions and kaons, so that we should be able to distinguish them from each other. For decay electrons and decay positrons, these are things that could result from certain collisions, but we see that the results lay directly on top of each other, and that means that they're produced at the same rate. We therefore can statistically cut the positrons, and then when we cut the positrons, these decay electrons that are being produced with them, we associate them together. Okay, that's cut as well. So that leaves out the unwanted electrons that might have been confused for the electron that scatters off of our proton. So again, we apply these cuts, and then we see that in the pink is the decay positrons and the black is the decay electrons. They directly lay on top of each other. So at all these different eta ranges. So we know that they're being produced together. These are things that we can statistically associate with one another. And then that means that that's out of the equation when we're looking at for elastic events. So given all this information, what we've done is that we've published these results now in arXiv, and also we will do so for the European Physical Journal C. We have done this type of study at the limit of 18 GeV electrons on 275 GeV protons, so even higher energies in the simulation. However, we observe that the reconstructed plots don't give us the same graphical information as previous plots. So basically, at such a high beam setting, we're seeing that we're in a whole different area of Q squared epsilon phase space. So this leads to different plotting. The graphs will just come up at flat at 0 or with no image. So that means that this provides us with future studies that we should look for at a different phase space, so that the we can have a guideline for the Electron-Ion Collider. So this will lead to further studies to confirm what range we should be looking at and what phase space. So I'd also like to mention that in my studies, I've been successful in doing work with Brookhaven's nuclear traineeship program, nuclear physics traineeship program. Currently working with Professor Deshpande at Stony Brook University still. And basically this study gives a good future and good reference point for the future of the Electron-Ion Collider by giving statistical guidelines as to what should be looked at when we're considering collisions at the Electron-Ion Collider. It relates to quantum sciences and quantum mechanics in a way that will help us to further understand quantum field theory and certain levels, gluons, especially in the strong force, strong interactions, quantum chromodynamics. It's the next QCD frontier. So just wanted to give a summary there. Thank you for the opportunity to speak about this. And thanks. I'll answer any questions that are in the chat or anything.
Yeah, so I also want to thank you very much. Personally, I think this was an excellent presentation, and I think you're an outstanding presenter. So let's see who has questions. You can write them in the chat, or you could just speak them up.
Yeah, I know it's a little different than probably a lot of the talks that are given, but it's a little more on the end of high energy. But
maybe. Yeah, but for us, it's a special opportunity. So if while people are thinking if they have questions or if they can come up with something, I would like to ask you a question which is not exactly directly related to the presentation, but I think is more related to your accomplishments and the fact that you are not only a member of the NSBP, National Student Council, but also president and founder of Stony Brook's chapter. So over time, we've tried to reach out to HBCUs and put a spotlight on, let's say, on NSBP researchers. And I tell you some names of the people that have that I've been in touch with. Some, for example, Charles Robinson, that could have tried, but we have not yet succeeded to actually set up at least one presentation that's focused on this, or to get people from those programs to come and present periodically in this forum. So Charles Robinson, who is at IBM, he was the chair last year. And before that, when I was chair, he was the vice chair. And he's tried hard. And I could just give you information on that. Tina Brower Thomas, if you know her, she, I think, is at Howard. She proposed a strategy, but she's too busy. I lost touch with her. And then there was Thomas Searless, who I think, I don't know if I'm saying the name right, but I think he's at Chicago at this point. So honestly, we've tried. And the question that I have is, could you help us establish a meeting with presenters that are specifically from, let's say, the organization that you are a part of? Do you think it's possible, like 2 presenters in September, do you think, or very difficult?
Oh, for sure. I actually know Dr. Searles personally. I just saw him. I was at KITP at UC Santa Barbara, the Kavli Institute for Theoretical Physics. So we saw each other. And Dr. Searles is very involved with HBCUs and IBM quantum initiatives. So I will talk to him for sure. The other names I'm not familiar with, but I wrote them down as you're speaking. So I definitely will do that. I will say that there is an HBCU, like maybe an informal network at this point, but becoming more and more formal, an HBCU Collider group that participates with Brookhaven National Laboratory. Right now, there's several interns at Brookhaven that are involved with scientific research. So I'll reach out to them. And also there is one other GEM fellow named Jordan Coney, who I'm familiar with. And he came from Morehouse University, is now going to UCLA for his PhD. I'm not sure of his research. I believe it was in either quantum optics or condensed matter, but that is somebody I would reach out to as well. So I mean, I can definitely facilitate this for sure.
Yeah. So Charles kept saying, we know there is good research. It's just not easy for whatever reason. Maybe our methods are different and wrong, to reach out and bring those researchers to present in this forum, which is something I would very much like to do. And then I will try to follow up with you or directly with the people whose emails you're going to provide to me, if you want to provide anything.
Oh, for sure. I definitely will. I will say that I guess the importance becomes directly just in being involved with NSBP, National Society of Black Physicists. We do have a conference coming up in November, which, we're always open to having people join and, present for their institution and give opportunities or speak to people. Personally, being a member of the student council and also being the president of the local Stony Brook chapter here, I just saw it like yourself. I saw it as an area where I needed to step in as a graduate student and help mentor some undergrads to actually attain this level of research and give talks and go to conferences. So
right. So it's good for you, but it's also good for people who will immediately see you as a role model and say, I too can do this. And I think this could basically take us to a critical mass point where we finally have the diversity and equity and inclusion that we want.
Absolutely.
Okay.
I don't know if anyone has any questions on the.
There is a question in the chat. So Artem says, thanks for the presentation. Could you tell us more about what is Pythia, Pythia, and how you apply it?
For sure.
Yeah.
Yeah, no problem. So Pythia is a software package that's often used with people at CERN. There's Pythia 6 and Pythia 8 are the most recent ones. basically, what we did here in this experiment, or this, I should say, this paper, is we create simulations of events, of these collision events, using Pythia. So it does simulations of events. It's not as complete as something like JAIONT-4, which is a full detector simulation. Nevertheless, it gets the job done, and then you can do smearing on it. And like I said, the smearing, it has a class of things called smearers that you make use of detector and device classes. But with the detector classes, basically, the smearing is representing acceptances. So things like the continuous regions of energy or momenta or angles, right? And then how do they perform, and how do they react to these events? How do the events coincide with physics observables? So basically what we're doing is using these two software packages to grant us very copious amounts of statistics, and then comb through those to see, okay, can we isolate the elastic events, meaning events where we simply have a proton going against an electron, they collide and bounce back off of each other, rather than inelastic events where we see all these other types of particles can form. A good example or a good illustration would be if you have a car crash. Sometimes, you just have a car crash where the two bounce off of each other. Sometimes you have a car crash where, where things fly out of one party's car or both parties' car, whatever. We don't want those events. We don't want anything spilling out or generating other particles. We want a restricted case of elastic events where they bounce off of each other. And that's why we comb through all these statistics and use these packages. And then, okay, Artem also says, would it make sense to implement that simulation of collision events using quantum computing? I'm sure it would become more efficient using quantum computing. There's probably, there's definitely things to look up with Monte Carlo methods and how they would be affected by quantum computing. So I would look into that. There's also, I believe there's some research going into Markov chain methods or something like that with Monte Carlo methods. So, Monte Carlo methods is a way of doing statistics that is king in high energy nuclear particle physics. So, if there's any research on quantum Monte Carlo, then I would say that would be the first place to start, for sure.
Okay, any other questions? Thank you so much.
No problem. Yeah, thanks for the question. Yeah, so I definitely appreciated all the questions. If there's any more I could answer, but also I guess I could put my email in the chat if anyone wants to reach out.
Yeah, there were some people who left, but they were asking me about your email because they said they had to go. So yeah, if you put your email, then I will send it to the people who asked me if I could get that to them, which I have anyway because I got it from Kim and Jake.
Right. So this Stony Brook email is my more permanent one that I'm putting in there, just because the Brookhaven email does expire once
I see.
Once I leave for after the summer, despite the fact that I'm associated with them as my GEM employer. So basically the Stony Brook one is more enduring, easier.
Yeah. Okay, I'll send it to the person that asked for it. Okay, so last call for questions. Any other questions? As we are approaching the end. Okay, if there are no other questions, I just want to thank everybody for attending today. This has been recorded. We will post it probably in about 2 days on the QED-C website. I want to thank the two presenters, particularly Alan, who just finished his presentation. Outstanding presenter and presentation. And thank you very much, everybody. Our next meeting is September 19, and we'll keep you informed as to the details. Thanks and have a wonderful rest of the day. Bye-bye.